Hello everyone. So in this session we will be covering some implementation part. We'll be coding transformers from scratch in PyTorch. So in this week what we saw was how transformers and the self-attention mechanism in transformer works. We saw different components of transformers like self-attention, multi-headed self-attention, then we moved to positional encoding, and finally we saw how layer normalization works. So we will put all this into practice, code this up in PyTorch. In the interest of time, I have already kind of compiled all the code that we are going to show today, and I will describe step by step every step, how we implement, and things like that. So let's start. So in the second week, we already, or in the third week, I guess, we already saw the basics of PyTorch, what are tensors, and how autograd works, how gradient descent is done, all these things. So now we will use all of those concepts to implement transformers. So for implementing, we import torch, which is the PyTorch library, and the torch.nn, which consists of all the functionalities we need to implement neural networks. As explained, device basically checks whether if CUDA stands for basically it's you can think of it as GPUs. Okay, so if you have some GPUs or graphics processing units available in your server, then Torch will kind of search it whether it is available in your current environment. If it is not available, we can use CPU. Colab provides some hours of free GPU access, but since this is a kind of toy exercise, we are not going to do some really large transformers. We're just doing a toy transformer model. So CPU will be enough in our case. Okay, so let's start by the self-attention module. So as we know, the paper which first proposed attention mechanism was in fact self-attention mechanism, because attention was already previously proposed for RNNs and LSTMs and sequence-to-sequence models basically. So self-attention was proposed in this paper. Attention is all you need, and we will be religiously following this paper for implementing transformers using PyTorch, right? So let us look at the architecture which the authors proposed. So we have already previously seen this diagram, but let us revisit this once before moving on to coding the part. So this is an encoder-decoder architecture in the same way what we have discussed in this week. Here, first, if you see the left-hand side block, that is a encoder block, right? So the encoder block consists of basically three modules, if you see in that way. First is the multi-head attention module, second is the feed-forward module, and third is the add and nor module. So focus on this left-handed block, right? So what it goes is, first you have inputs. So inputs are like NPTEL is great, right? This is a text input. And then we have a input embedding, so first this text is tokenized. So we have already seen the tokenization algorithms, different tokenization algorithms like byte pair encoding, like sentence space tokenizer, word pace, all this we have seen. So first the text is tokenized. So suppose NPTEL is great, we will see this in practice in subsequent weeks when we discuss in the Hugging Face library and Hugging Face tutorial. There we'll explain and show how tokenizers work basically in practice. So suppose we have this text, NPTEL is great, and for now let us assume it is tokenized as NPTEL is a single token, is a single token, and great is a single token. Now each token is then passed to an input embedding layer. So what input embedding layer does, it is basically kind of a lookup table, where for every token in the vocabulary which is already present, we have a embedding. Embedding is basically a vector representation of the token, right? And then we add positional encoding. So in this paper, they proposed, as we already have seen, the sinusoidal positional encoding. If we see here, right, this. So the sinusoidal positional embedding, what it says is, so it's sign of position by some number to the power 2i by d module, right? And it alternates for each dimension between sine and cos. So this is a kind of static positional embedding, static and absolute. Static in the sense it is already predefined for every dimension, dimension I and every position POS, and every dimension I, it is already predefined, right? It is not trained explicitly. And it is absolute in the sense it considers the absolute position of the token, right? Whether it is at 0 index, whether it is 1 index, and like that. So it is not relative. So gradually we saw how there are propositions on trainable positional embeddings which are dynamically updated during training, and also relative position encodings which takes, instead of taking the relative absolute position 0 1, it takes the relative position between the tokens. So we have already seen this all this in this week, right? So this multi-head attention so takes in 3 inputs: the query vector or the query matrix, the key matrix, and the value matrix. For the encoder part, all the query, key, and value comes from the input, right? Whatever the input we are giving, after getting the input embedding, addition of the positional encoding, we have, say, vector matrix X. So Q, K, V, query, key, and value matrix, all are coming from the same input matrix. Then multi-head attention gives whatever it does, we will see that again. Then it is add unknown. What it does is there's a residual connection. So the input matrix is again added to the output of the multi-head attention. We apply a near norm on top of it and then pass it onto a feed forward network. So this is a encoder block, a single encoder block, and it is stacked n times. So there are n encoder layers, right? And then we have the decoder, which we'll see next. So now so what is the main part of this? The main tough part, where you need to do a lot of thinking how to implement it, is basically the multi-head attention part. This is multi-head self attention. So we will see this module first. So this class, right? This class self attention implements that multi-headed self attention part, right? So for any class, hopefully you have already done the prerequisites for Python and object-oriented programming. So you must know that whenever we declare any class in any object-oriented programming language, be it C++, be it Python, be it Java, we need a class constructor, right? So the class constructor basically defines how we're going to handle the different attributes of the object which will be instantiated from the class. So this init method is basically an basically it instantiates the class, right? It is a constructor method. So our embed size is basically the model embedding size, right? So if we want to draw parallels with the paper, if we see here, okay, so let's see the multi-head self-attention section. So here you can see that this D model is basically the embedding dimension, and this dimension is consistent throughout the model. That is, each layer output is of dimension D model. So this D model we define as our embed size, right? And heads is the number of attention heads at each layer, right? So what will be the head dimension? If we see here, so it says that dk and dv. So dk and dv, dk is the dimension of the key and the query. So the key and the query vectors, or when you stack vectors, it become matrices. The key and the query matrices always have the same embedding dimension, right? So this dq and dk are basically same. So dk is the key dimension and dv is the dimension of the value vectors. So what is it? It is D model by H. So D model is our embed size and H is the number of heads. So that's what we do. Head dimension is embed size by number of heads. And we write a condition, an assertion condition, to check that the embedding size, right, so the embedding dimension should always be divisible by the number of heads. So when you multiply the number of heads and our head dimension, we should get the embedding dimension. So this is a kind of assertion. And we define 3 layers, linear layers. Basically, linear layers means a simple linear transformation, multiplying a projection matrix. So if you have kx, it is just writing wx. So that is w is our learnable matrix. So that's what linear layer does, right? So maybe I can write here. So what linear layer does is, if you have a input, say x, then what after passing on this linear, right, what it will does is it will just make it wx, right? So this w, where w is trainable, right? W is a trainable matrix. And we define such linear layers for every values, keys and queries. And this fc out is basically where we multiply wo. If you see here, after concatenation, we multiply another matrix wo, right? So that's what this fc out does. You can say it as wx, or in our case it's basically xw, right? So it's xw, so this fc out is basically then wo. So whatever after concatenating the head outputs, we apply w on top of it, right? This is what fc out does. Now let's look at how to define the forward pass through the self-attention. So as I said, what is the input to the multi-headed self-attention module? It's three matrices: the key matrix, the query matrix, and the value matrix, right? So we define n as the first dimension of the query matrix. So what is the first dimension of the query matrix? The query matrix, if we will see in details there later. So the query matrix, whatever we have, this query is basically up shape. Shape is basically the dimensions of the matrix, right? So first is n. So what is n? N is the number of training examples, number of examples in a batch, right? And then we have how many tokens are there in the query. So we can define it as query len, right? We can define it as query len. Then we have the embedding dimension, right? Embedding size in our case. So this is a query, how it is going in. And so, okay, after that, what do we do? Look, so you have the QKV, you pass it through a linear layer, each of the matrices. So these linear layers are defined here, these three linear layers, right? And then we have n, which is the number of training examples in the batch, and this value len, key len and query len are basically the number of tokens in the query matrix, the key matrix and the value matrix. So number of tokens is defined as basically this query length, what we are saying, right? So now, because look, in the encoder case, the query length, key length and value length are the same, because all the query key and value comes from the inputs. In case of decoder, on the other hand, the query comes from the input to the decoder, but the key and values come from the encoder module, right? So the key and value may not have the same length as the or rather in most of the times don't have the same length as the query. So that's how we handle it explicitly. And when we have this key query in values as n, which is the number of training examples, say len, which is the number of tokens, and embed size. So this embed size is now basically, if you think of in that way, this is heads, number of heads into head dimension, which you already saw. So we need to break this up into different heads. So we have already multiplied it by the projection. Now we divide it into different heads explicitly, right? So we do that here. What we do is we reshape the in Torch there is this concept of reshaping tensors. So we keep the first two dimensions same, right? it's n and value length, key length, query length, whatever it is, and we divide the embed size into number of heads and the dimension of each head. So the multiplication of this last two dimension, so we already asserted the self dot heads into self dot head dimension, which is the dimension of the individual heads, is equal to self dot embed size. We already made that assertion, right? So now we have the key, query, and the value matrices passed through the linear layer, so it's different for every heads, right? Now, how do you calculate the attention scores? So this is how we calculate the attention scores, right? So this part we call attention scores. So it is qk transpose by scaled by the square root of the dimension of the keys, right? So let's first focus one by one. So first is qk transpose. Now let's think, when you have a normal query and key vectors, right, where q is basically, say, your number of tokens and dk, right, and your k matrix is also the number of tokens into dk, number of tokens comma dk basically. So if these are your shape of q and k, then it's pretty easy to do qk transpose, right? Qk, let me write qk dot t. So this is qk transpose, and so we already have, suppose we have the q matrix of which is just basically, think of it as a single example, right? A single sentence. So q matrix is of say n tokens is the number of tokens, comma the dimension of the key vector, because q and k have the same dimensions, and the k vector or matrix whatever is simply the number of tokens and comma the dimension of the key. Then we can do simple a qk transpose, which will give us basically attention map or attention scores of dimension of a square matrix with dimension number of tokens, common number of tokens, right? But when we have this batch, right, when we add this n over here, right, n over here, then qk transpose doesn't work as intended, right? So now what do we do, right? So so there is this method called Einsum. Okay, so Einsum is basically a more generalized function for doing matrix multiplication. So what you give as input to the Einsum are your input matrices, and as a rule you explicitly tell what are the dimensions of your input and to what dimension do you want it to map to, right? So this is a more generalized matrix multiplication. So for example, here n is our number of sentences in our batch, q is the query length, right? Q is the query length, h is the number of heads, and d is our head dimension, right? So tell me, what is the shape of the query vector? It's n, right? Then the query length q, then the number of heads, just look here, n, query length q, number of heads h, and the head dimension d. So this is how we represent the dimension of the query vector when passing it to Einsum, right? Similarly, tell me what is the dimension of keys. It's n, the number of training examples. Key length is different from query length. It can be different in generalized case. So let us call it k, right? And the number of heads are the same h, and the head dimension is same d. So it's nkHd, right? This is the dimension of key matrix. And we want to map it to attention scores. So what should the attention scores give? For every sentence n, right? We should have, so for every sentence and for every head, right? For every sentence and for every head, we have an attention map, right? So ponder upon this very carefully, that when we are giving a batch of sentences as input in a multi-headed self-attention, at the first step, what do we have? We have a square matrix. So the square matrix, the y-axis, in the y-axis, we have the keys. So NPTL is great, right? So for every token, say NPTL, right? We have a attention scores over each token in the sentence. So for NPTL token as query, all the three acts as keys, right? So we have attention score for NPTL, we have attention score for ease, we have attention score for great, right? Say it is 0.5. So before normalization, before converting to probability, it can be anything. After converting to probability, when we apply softmax, it becomes something like say 0.5, 0.3, 0.2, just like that. So then what is the dimensions of the attention score matrix? It is the, for every n number of training examples, for every head, we have a matrix where the number of rows is the y-axis, which is the query length, and for each query, we have attention distribution over the keys. So it's n, h, heads, q, and k, right? So this is a mapping we need to do. So now Einsum tells what do you give as input to the Einsum? If you give the input 1, the dimension of input 1, comma, the dimension of input 2, give an arrow like that, right? Give an arrow like that, and tell to what you want to map it to. So we need to map it to NHQK as we discussed here, and the inputs are queries and keys. So maybe I can illustrate a little bit to give you an example that Einsum occurs in similar way to matrix multiplication, right? Suppose I have a torch dot tensor. Let us take a 1, 2, 3, right, and say 4, 5, 6, right? So this is basically A. So what is A then? You see A is a tensor, and what is the shape of A then? Shape of A is, so it's 2, 3, right? 2, 3 dimensional tensor. Now we have say a B. So let us copy this. Okay. So define another tensor B, and it is say, it is something 3, right? So it should be say 1, 2, 4, 5, and 6, 7. So what is the shape of B? The shape of B is 3, 2. Okay, so now A and B are fit for multiplication, and upon multiplication, what should the dimension? 2, 2. So if we do a simple matrix multiplication, so this is basically matmul. Let us call it matmul. So this gives us some basically so let us print that too. So we can print say normal matrix multiplication, right? Now suppose we want to do Einsum, right? So let us say Einsum. So in Einsum, what will you do? Tell me. So you should do things along with me. You should also have a laptop and open your basically collab and just do with me. So okay. So when you Einsum, what do you want to give? Tell me. We already discussed. So we have a rule, right? A rule. What is the mapping? So what is the dimension of A? Say it is PQ. And what is the dimension of B? So the number of columns in A must match with the number of rows in B. So say it's QR. And what is the mapping rule? We want PR. So this is the mapping rule in case of matrix multiplication, right? And what are the inputs? It's a comma b, right? Similar to what we did here, correct? And now let us check whether if we do Einsum multiplication and if we do matrix multiplication, are the results same? Let us check. So you can check, you can see by normal matrix multiplication and by Einsum, we get the same output, right? So this is a kind of a small illustration on how Einsum works. Einsum can be helpful for dealing with more generalized, more complicated things, but this is just an kind of toy example to illustrate that, right? So let's go back to our self-attention code. So till now, what we have is our attention score matrix, right? So the attention score matrix is of shape, number of training examples n, right? Number of heads h, and query length cross key length. So this is clear till now, right? Now we define a mask. Why do we define a mask? Because suppose the number of the sentences, the different sentences in our training batch are say not of equal length, right? Suppose the first sentence is of length, the number of tokens is say 5, second sentence is 10. Then we basically pad some special tokens into the smaller sentence to make the two sentences of equal length. Sometimes we can also truncate, whether we can decrease the length of the larger sentence. So it's upon us. But generally we use both truncation and padding. So we truncate the length of the maximum sentence to a particular input length, say like 512. And if any sentence is lesser than 512, we pad with some special token to make it 512. And if we have sentence greater than 512, we truncate it to 512. So that is how we generally handle batches to make them of same length, right, for parallel processing. So what this mask does is, if you have 0 in a mask, so we will later, when we run this, we will see how we define that. If we have a padding token, make it a 0 index, right? So if you have a 0, what it does is, it makes the attention score in place of that mask token, as when this mask token is the key for a particular query, the attention score is made basically a large negative number. So when you have a large negative number, think of it as a minus infinity. So when we apply softmax, it becomes 0. So the model does not unnecessarily attend to the mask tokens, right? So this is kind of a way to handle that the model does not pay attention to the padded tokens, otherwise training will become noisy. And then finally, once we have the attention scores, as we saw here, we first scale it by the square root of the number of square root of the head dimension. So that's attention score by self head square root of that, and we apply softmax to it. Where do we apply softmax? We apply softmax on dimension 3. So what is dimension 3? So this is 0 dimension, 1 dimension, 2 dimension, 3 dimension. Third dimension is the query key length, right? Key length. So applying softmax over dimension 3 tells us that for every query index, so what is for every query index, that is for every query token, we have a probability distribution, right, over the keys. So that's what attention does. And then again we use Einsum. So this is again a simple matrix multiplication, but it couldn't have been handled by a simple matrix multiplication. So what this out is doing is, after we have this softmax of this, we just need to multiply with it the value matrix, right? So so the input is basically the attention and the value matrix. So what is the dimension of the attention? Okay, so attention dimension is the n. N is the number of examples, h is the number of heads, q is the query dimension, and L is the k dimension. K, that is the key dimension. Dimension of the basically not key dimension, it is the number of the keys, right? Number of key tokens, key length. And one thing you should always note is the key length is always equal to the value length. So the key space and the value space are defined over the same set of tokens, right? So the key length L and the value length L are the same, right? It was K previously, we just made it L to make it generalized in both cases, right? So what is the shape of the value? It's N, its value length L, number of heads, number of dimension, and finally what we want is for every sentence we should have NQHD. That is, for every sentence we have the key query length, the head number of heads, and number of dimension. That is, again, we want to restore after multiplying with the value matrix. So the final output from the from each head is same to the final is the dimension of the final output is same as the dimension of the initial input, query input we gave, right? So this makes that, and after we have the output, so this part, what is the output? It's the N Q H number of heads and D the head dimension. Now we want to reshape it. So why do we want to reshape it? We want to make it basically we want to concatenate all heads, right? So concatenating all heads means this H and D. So this N and Q remains the same. This H and D are merged, right? So basically this operation, this concatenation of each head, right? So this H and D are merged to heads into head dimension, which is the embedding dimension. So finally, you can check, maybe I can comment this for now. So attention scores dot shape should be the N, query length, and the embedding dimension. We simply apply the FC out. FC out is basically applying the WO matrix, right? And we return the output. So now we have this whole multi-head attention module implemented all over, right? We implemented the whole multi-head attention. Now the stacking up for encoder and building the decoder is easy because we have this main part done. So now we can quickly go through how we finally do the encoder. So for each encoder block, we call it transformer block. Why? We will see, because this part can be reused while writing the code for the decoder. So what we have once we have the multi-head attention, we take the add and norm and apply it to feed forward network, right? So we define two norms, norm 1 and norm 2. So this is norm 1 for norm after the multi-head attention and one norm after the feed forward network, right? We define a simple feed forward network using ln.sequential. If you're not familiar, you can look up the documentation and read what ln.sequential does. So it's simply a linear layer followed by a ReLU activation function and another linear layer. What this forward expansion does is, so suppose you have first embedding dimension of D as input. The forward expansion, that is the first feed forward layer, up projects it. Now what is the up projection dimension in this paper? So in this paper, they have taken the forward expansion factor to be 4. That is, if the input dimension is D, after up projection, it becomes 4D, right? And then from 4D, it again down projects to D. So that is what we do in this part, right? We first map it from embedding dimension to forward expansion into embedding dimension, embedding size. So forward expansion can be defined as 4 as in the paper, and then we apply a activation function and then again down project it from 4D to D, right? And then we apply a dropout. Dropout is just for regularization, so it doesn't overfit during training. So what does the forward function do? We have the attention. So we have the query key and value matrices and the mask with the padding, which ensures that it doesn't attend to the unnecessary padding tokens, special tokens. So then this attention plus query is basically the add part. So if you attention is the input to the multi-headed self attention block, right? So the output is again attention. So you can see here attention. So self dot attention, when you pass value, query and mask, the output is attention, right? So with the output of the multi-head attention, you add the initial input query again, right? This is the add, right? And then you apply the norm on it. So this X here is basically after multi-attention and add and norm, right? And then what you do, you pass X to feed forward and again add and norm. So what you do, you pass X to feed forward layer. This is forward, and then you again apply the norm. First you add it, so forward is the output of from feed forward and x is the input to the feed forward. This is the add operation, and then you again apply null norm, and finally you get the out. So this completes our encoder block. Now for the whole encoder module, what you do, you basically stack n n encoder blocks, right, on top of the other. And what is the input? The input is, you have the word embedding, you add positioner embedding to it. So we have taken a more simpler trainable positional embedding layer here, which is trainable. So the embedding is defined over the max length of the input and the embedding dimension, right? And the word embedding is embedding, and not embedding is basically a trainable dictionary lookup table kind of a thing, right? So the number of keys are the vocabulary size, and the embedding dimension. So maybe we can quickly go through this, that we have a module list, right? So the module list, what it does is it stacks n modules, right? So this transformer block is stacked n times. So what does stacking mean is the input, you give input to one block, and then the output of one block, output of the block acts as the input to the block on top of it, right? So we stack that, we add a dropout. So if you look at the forward function, so first you have the x, which is the input. So x is basically a matrix. Number of rows is the number of training examples in the batch, and sequence length is the number of tokens in each sentence, right? So positions are basically 0 to the word length. These are used for positional embeddings. So what you do first is get the embedding of each token and add it to the positional embedding, right? And then for layer in self.layers, that means for each encoder block, you pass on the final out. So what is out? Out is x plus positional embedding of x, right? So you pass on that. So the key query and value, as I said, the key query and value for the encoder block is the same. It's the input embedding plus positional encoding embedding, that matrix, right? So the key query and value comes from the same matrix in case of encoder. On the other hand, for decoder block, right? So for decoder block, everything is same. Only difference is that the key query and value, the query comes from the input and the key and value comes from the encoders, right? The first attention, which is the masked multi-layer attention, this masking is done on the future tokens, if you remember. So the transformers can't see the future. We should ensure the transformer shouldn't see the future, because generally transformer can see the future if you give the whole target sentence as input. So we must make sure that the future tokens are masked as keys and values when we are handling a particular token as a query, right? So they shouldn't be able to see the future. So that is the first thing, that is the masking. And this masked multi-attention takes as input the input to the decoder, right? So the first attention block takes as input the input to the decoder, and then we apply the add and norm again, similar to that, and then we apply, this is the cross attention, right? Cross attention, the key and the value comes from the encoder and the query comes from the decoder input. So so basically when we stack these layers, so in the decoder again we have the word embedding and positional embedding, we stack the n layers, right? And this is the feed forward, basically FC out, you can similar to what we did in encoder, and we add a dropout. So this is the input to the decoder, the positions. So what we do is we first take the word embedding, add the position embedding, add a dropout, and then for every layer, what we do is basically we just pass on the current input to the decoder, the output of the encoder, and the source mask for masking the padded tokens, and the target mask for masking the target mask is basically for masking the for the tokens, as we said in the decoder, what is the masking? The future tokens, right? So target mask marks the future token. So the transformer can't see the future in that case. And this FC out is basically then projecting the whatever output you have. So this FC out is this final linear layer, right? It projects from the embedding dimension to the vocabulary dimension, and then softmax makes it a proto distribution, right? So this FC out is basically projecting from embedding dimension to the vocab size, right? And this completes the decoder, and the final part is using all this. So when we use all this, what happens? So we have an encoder, we define, just like we said, so there are n encoder modules within it. We define a decoder, we define the padding index, right? Padding index for input to the encoder, padding index for input to the decoder. So this takes care of the pad tokens, and this takes care of the future token masks, right? And then we have device. So then we have the source mask. So what does the source mask do? For all places where there is 0, so we'll define the pad index to be 0. It's a source mask, so it's 1 everywhere, and wherever there is a padding token, it's 0. And previously we saw how we make it minus infinity in the attention metric. Similarly for target mask, so trill is basically a lower triangular matrix, right? So for the, as we have seen in the lecture, for the target mask, what we have, it's a lower triangular matrix. So the lower triangular matrix is 1, and the upper triangular matrix is basically minus infinity in the attention score. So we make it a 0 here, and then in the mask it makes wherever it is 0, it is minus infinity, as we discussed in the the code. And then simply we pass the forward function, the source mask, target mask. We get the output from the encoder using the self-dot encoder, and we pass the output of the encoder to the decoder along with the input to the decoder. So just to show, suppose we have a basically a tokenized input, right? So this is, say, a tokenized input of dimension 2,9, and then we define the source and target pad index to be 0 and the vocab size to be 10, right? And then if we apply input this x, input x, the target vocab size, source vocab size, and all this to the transformer, it will process it. So maybe I will run this once to show you that it works fine, right? So this print that is working on CPU, there's a printed device over here, and then the torch dot size, that is 2 is the number of example sentences, 7 is the number of output tokens, and 10 is basically the output vocabulary size, right? So this is a kind of walkthrough to how we can implement transformers in PyTorch. We could do more things like define the position encoding using rope and things like that, but this must be helpful for you to at least get started with coding transformers in PyTorch. Okay, so that's it for this lecture. Thank you, enjoy, and happy learning.